class, we're going to now proceed to look at a new topic, electromagnetic waves. Electromagnetic waves, and we think of these often as waves that travel through the atmosphere, and they are energy. The waves are energy, but this energy requires no transfer of matter at all. So this transfers energy, and it's an energy transfer that requires no matter. In other words, this can go through space. It's different from sound waves. Sound waves are wave energy, but they require matter to go through. If you knock on wood or you knock on a door, you can hear the sound. It's because the air, the waves travel through the air is compressed by the knocking, and then that compressed air, these waves, compression waves, reach your eardrum and you hear them. So that's different from sound waves. Sound waves, by necessity, need matter to travel through. So sound will not travel through space where there's no matter. So when you see a Star Wars battleship blow up off Alderaan, and you see it blow up, and you hear this big explosion, that's totally bad information. Looks great for sound effects, but it's bad because that doesn't happen. You don't hear things blow up out in space. Sound does not travel. So waves are measured, and we want to review this a little bit and then look in your book. Waves are measured, and they have several parts. There's a crest. The wave crest is kind of like the high point of a wave. The low point is called a trough. And the distance that a wave rises or falls from its normal position is called amplitude. So we have wave amplitude. This is the distance from which it rises or falls. And then one wave basically consists of a trough and a crest. It's like a cycle, and it consists of a cycle of a wave, a trough and a crest. So let's go ahead and make a diagram and kind of outline that. Now there's this baseline that just shows the existence of no waves. And then we've got a wave sign, or a wave that passes by. And of course this is a crest. It's the high point. I'll put a C there. This is the trough. And so from a crest to the next crest, the next high point, that would be one wavelength. And the symbol for wavelength is the Greek lambda. Okay? So this is a wavelength. Now you could also have a wavelength from a trough to the next trough, right? Wherever that is over here. That would be one wavelength, and it's going to be the same distance as from crest to crest. So notice that this is still one lambda. It's still one wavelength, okay? And so one wave is called a cycle. And so what we're going to do is ask you to go to your book and turn to page 460. On page 460 of your textbook, you can see a very cool diagram, and you can see the wavelength. It's showing from trough to trough, but it's showing what amplitude is. So the amplitude would be how far the wave goes from the baseline. So this would be an amplitude. It'd be this distance from crest to the baseline, or this distance from the trough to the baseline, okay? And that would be the amplitude, okay? Now the number of wavelengths that passed a given point in 1 second is called a frequency. So if you have lots of little tiny waves that have a small amplitude, notice you're going to have more of those pass in a second. So that's going to be high frequency. Now low frequency is going to be your longer waves that are fewer wavelengths in one in 1 second that pass by. So scientists measure the frequency in units called hertz. And so you'll hear kilohertz, which equals 1,000 cycles per second, megahertz, which equals 1,000,000 cycles per second, or just 1 hertz. 1 hertz is equal to 1 cycle per second. So hertz is the measurement of the frequency, okay, the frequency of the wave. So we see the height of the wave is measured by amplitude, and the frequency is the number of cycles per second. And 1 cycle per second is a hertz. So they're measured in hertz. Now waves move very, very quickly. Okay, so they're very fast moving waves. And the velocity of waves is really mathematically related. So the speed or the velocity of a wave, okay, is equal to the frequency, and that would be measured in hertz, times the lambda, the wavelength. That would be your velocity. Okay, now on page 461, there's an example problem, and it says, suppose that waves on a beach are arriving 1 every 5 seconds, and that the space in between them is 20 meters. What is the velocity or speed of these waves? So to measure that, the velocity is going to be equal to your frequency times the wavelength. Okay, your frequency is 1 wave per 5 seconds, or 1/5 wave per second, or 1/5 hertz, right? And then, of course, your wavelength is 20 meters. And then your unknown is the speed. The speed is the velocity. That's what you're looking for. So you use the formula V, the speed, is equal to the frequency times the wavelength. And you have, by substitution there, if you have the frequency is 1/5 hertz and the wavelength is 20 meters, 20 times 1/5 is 4. So the velocity would be 4 meters per second. So that's pretty easy, okay? Now, we have a lot of different kinds of waves, and what I'd like to direct you to is to look over at 465. Page 465. And on page 465, we've got more information on the spectrum. So as you can see, an electromagnetic wave is the combination of a magnetic and an electric field moving at right angles to itself. And so they have a great diagram there on 465. So these electromagnetic waves are basically a combination of a magnetic and electric field that move together at right angles to each other. See if I can spell that a little bit differently. At right angles to each other. And so there's a great illustration. I love that illustration on page 465. Now on 466, you need to be familiar with the different kinds of electromagnetic waves. Notice the frequency. Now the frequency is going to be, remember how many waves per second. So if you have 10 to the 25th, that's 10 times, or 1 times 10 with 25 zeros after it. So you're looking at billion, trillions of waves. So those are tiny, tiny waves. So the wavelength is really, really small. So at the top of the page, you can see gamma waves are the smallest. And look how tiny the wavelength is. The wavelengths are so close together, they form a red band. So the band is almost solid. So you should be familiar that gamma waves are your smallest waves, but they have the greatest frequency. So they have the smallest wavelength. They are very close together, but because they are so close together, lots of them travel in 1 second by a certain point. Notice that the next longest waves would be X-rays. X-rays are still very small waves. They have small, but they're larger. They're larger wavelengths. There's more distance between crests and troughs than with gamma waves. Okay? And then we get to ultraviolet light, UV light. UV is a little bit larger wavelength. And then we hit visible light. There's the light that you and I can see, that visible spectrum. So we can see blue and orange and yellow, okay? So that's great. That's visible light. So visible light is a part of the electromagnetic spectrum. So what we see with our eyes is actually wavelengths of energy that is from the sun, and it reflects, that light reflects off objects, and we see them as color. Now look, as the wavelength gets bigger and bigger. Okay, so the longer wavelength. So wavelength is going to increase. Here's the wavelength. It's increasing as you go down this way. So X-ray, gamma rays are going to be really, really small. Okay, so we then have infrared. A little bit larger wavelengths. Then microwaves. Micro, of course, means really small, but actually they're pretty large wavelengths. It's kind of a misnomer. Then we have short wave radio. Oh, shortwave radio. Long, long waves. And then finally, long wave. Long wave radio. So they're your longest waves. And of course now, if you get all confused, look at that kind of the band to the right on page 466, that red band, and you can see at the very top, very short wavelengths. They're so tight together. And then way at the bottom with the radio waves, a lot of distance between the wavelengths. So with more distance, there's less frequency. With less distance, shorter wavelengths, you're going to have higher frequency. Okay? So that's important to be familiar with that. Now, you're reading about each of these types of waves. So you want to read, and so that you learn and understand about these. But let's flip over to page 475. Now, light, which is your visible spectrum, is shown there on page 475. So, for that visible spectrum, 475, you want to be familiar with that we have this rainbow spectrum. And it starts out with red on, it doesn't really, I don't care that you know which is longer wavelength, but, to be honest, the longer wavelength is red, so this is the longest. A little bit shorter wavelength is orange, and then yellow. So I'm just going to use these terms as an acronym. Then green. So you have a green, and then you notice it goes into blue. Then you have indigo. Indigo is almost a purple. And then you have violet. So here's your electromagnetic spectrum. This is the longer wavelength. I don't care that you know that, but it's probably good information. This is the shorter in our visible spectrum on this side. But notice it really spells out a word, Roy G. Biv. So if you can remember Roy G. Biv, you've got it. Okay, so that's what I want you to work on. Now, on page 476, you can see that there's again, the spectrum. And you can see the red is the longer wavelength. And it's a wider band. And then violet is your shortest, okay? And then we can see that, and there's a good little frequency there, a frequency diagram above the color diagram. And you should notice about color perception. And as you read this section, to realize, that we perceive these colors because light is reflected off of the colors, and they come back to us, and the colors, blended colors, like on page 479, you have primary colors, the red, the blue, and the yellow. And so that's really yellow, magenta, and cyan. Okay. And then, of course, if all of those are blended together, and added them together, you get white. So white is a blending of all the colors of the rainbow. Black is an absence of color. Okay. So, so when you add them together, that's what you get. So, let's take a look over at the speed of light. Now, the speed of light varies as it goes through different mediums. Down at the bottom of page 479, we can, the speed of light through air is, notice, 300 million meters per second. But it slows down as light goes through water, and slows down even further as it goes through glass. So the speed of light can be slowed down as it goes through different medium. Okay? And then intensity of light is another thing. Light is more intense when it's close up. Let's look on page 482. And we want to look at intensity in this little section. The intensity of the light, as you see in figure 2018, is that the further away you get, of course it gets less intense, but it's inversely proportional. The intensity is inversely proportional to the square of the distance from the source. So let's see if we can understand that. Look at that light, flashlight in the picture, and that first square, it's 1 meter squared, 1 square meter, and it's out at 2 meters. So it's, 1 meter away from the flashlight. So all the light is hitting that square, and it's very intense. Now, as you back that square up to 2 meters out, you notice that the light, that same amount of light, is hitting 4 times the area. It's 4 square meters. So it's squaring the area each time. Okay, so if you back out to 3 meters, so every meter that you back out, there's a squaring of the area that the light is covering, so it's less and less intense. So it's like you double the distance back, but by doubling the distance back, you make the light 1/4. That's the inverse squared. Okay, we call that the inverse square law. So that's just shows you that as you back light away, as you get further away from the light source, it doesn't just go down, but it goes down exponentially. The light intensity goes down. That's called the inverse square law. Okay, so that's good to understand. Now, Jaden, I remember, did her project in science on reflection and refraction. And I'm not going to go over that section, but that's the next section. You may want to look at that as rays of light go through a medium like glass or plastic or air or water. They get bent. They're refracted. That's what refraction means. So a reflection would be like light bouncing off a mirror, coming straight back. Refracted is when it actually gets bent as it goes through a substance. So if you look on page 489, we're seeing light refracted. There you see it in water in the beaker, and because it's bending through the water, it makes the ruler look like it's offset. And you can see on the bottom of 489 how light is refracted, and so it appears to bend as it goes through, and actually does bend as it goes through a substance. So, so an interesting passage. Now, we are going to take just a few minutes to talk just a little bit about basics of electricity. So let me give you electricity. Of course, electricity is a flow of electrons. Okay, everybody knows that. We've talked about that in class. Electricity is a flow of electrons through a wire, right? But there's actually three basic types of electricity. So let's outline those. Number one is static electricity. And static electricity, of course, all of us have experienced that as we've scraped our feet along a carpet and we touched a doorknob. We built up a charge of electrons on our body. We kind of knocked them off the carpet onto us, and then it discharged when it went to a metal object, like a doorknob. So that is static electricity. Another example of static electricity is the idea of lightning. So lightning is a buildup of electrons, and in a cloud there's because of the movement of warm air, particularly in the summer, we have lots of lightning storms. The air actually builds up an electron charge, a negative charge on one side of the cloud. So this normally happens in a thunderhead, a big tall cloud. So one half of it gets negative charge, the other is positive charge. And then magnetism is a second form of electric energy. Electricity, actually. So magnetism is a field of force around a magnet. And if we turn a wire around a magnet, we can create a current. So magnetism is a form of electricity. It will create a current if you turn a wire around a magnet. And then thirdly, we actually have the old faithful electric current. All of us have probably been shocked. We've stuck our finger in an electric socket or the top of a lamp, and we got shocked as we had that run through us. I hope none of you were standing in water or standing in the tub when this happened, because then you are the electric current will go through your body, and it could damage something. If it goes through your heart, it could stop your heart. It goes through your body and it burns, through your body, which is mostly water, but you also have a lot of ions. So, it's easy for the ions to transmit electricity as it goes through. But if you're standing in water, it wants to head toward that water, or if you're standing on a metal surface, it wants to head for that. So you want to be very, very careful. Don't ever use an electric appliance when you're in the bath, or don't try to change a light bulb when you're standing in water or something. Don't try to fix an appliance if the floor is wet. So you have to be sharp and be careful, because people do die from being electrocuted. So the three types of electricity is the current, magnetism, and static electricity. Probably the most famous person in the history dealing with static electricity is Ben Franklin, of course, who amazingly was not killed when he did his lightning experiment, and he put a kite up in a thunderstorm, and the silk line that he was holding was attached to a metal object, and so lightning struck the whatever you call it, the kite, and it went down the line, the silk line that was wet, and it of course was grounded into that key, so it made the key glow. But it could have gone through him, it could have gone into his hand. If he was standing on wet grass, it could have gone through his body, and it didn't. And honestly, I'm trying to remember, I've read that account in his autobiography. I'm not sure if he says he was even shocked, but he was holding it in a glass jar, and so there was some insulating property, okay? Now, guys, especially the young guys in this class, do not try to replicate his experiment. I know you're thinking about that. Do not think about that, okay? Just kind of force it out of your mind. Do something safer. Go study it. Do not try it out, okay? So please don't go out there and in a rainstorm and try to see if you can replicate that. Now, of course, the whole thing about electricity is that the atom has electrons. And you guys remember, these electrons are found on the outside of the atom, and these electrons in that outer shell, valence electrons, are easier for the atom to add or remove. And we know that because we know they come off. The valence electrons will jump from atom to atom. Okay? We actually did a lab where we saw the heated electron jumped, and as it cooled, it emits light, and we saw it emit these beautiful colors as we burned up different salts. Okay, I don't know if you all remember that, but that was that same thing, these electrons jumping off the outer shell and then jumping back and cooling or giving off light energy. So they can be removed or added, and when we do that, we create ions. We get anions if there's a negative ion, or cations if it's a positive ion, okay? And so these charged particles will either attract or repel other charged particles. So for instance, if we have two negative particles, they're going to repel, like charges repel, opposite charges attract. So if we had a plus and a minus, they're going to attract. Okay, so this is the charge that is used there in, between different atoms. So this is what makes electricity flow, is that these charges either attract or repel. So we're going to just begin one last part, but it's going to be a short part as we cover a few things about batteries.